So as John said, I'm Rob Slater, co-founder of Redshift Rendering Technologies. We make Redshift, which is the world's first biased production-ready GPU renderer. And this talk, we're going to tell you a little bit about how Redshift has improved over the year. So 2017 was another very good year for us. We're still a relatively new company. We saw a big customer increase in large studios and small studios and freelancers. So we realized that because of this increase in customer base, we had to basically do something about add better customer support. So we basically expanded the team. We've got more tutorials, better documentation, and we've decided to focus stronger on better DCC integrations in general. So first off, 3ds Max now has a dedicated plugin developer. He's been listening to the 3ds Max community to basically make the integration stronger, less quirky, add more features, and he's also been working on better third-party integration support as well, for things like Forest Pack. C4D, our plugin was new last year, and this has been maturing very nicely. We've had lots of valuable feedback from the passionate C4D community. So we've been adding some cool new features like an asset manager and an AOV manager. We've also been listening to the concerns about scene scales, which are kind of different to say Maya, for example, and how that affects lighting. So very soon we're going to be adding a scene scale control, so you don't have to have crazy lighting values to get good looking lighting. Houdini plugin is going from strength to strength. And one of the recent things that we added is Houdini style sheet support, because those Houdini artists really love their flexibility. And Katana as well is also pretty much feature ready. Got tons of features now, and it has built-in Alembic support. And finally, Maya has seen some improvements in interactivity for an almost real-time feel, especially with camera movement and stuff like that. And I should note that all the interactivity improvements that we've been working on are across all DCCs and all operating systems, and this is something that we're going to be continually working on over the next few weeks because we want it to be almost real-time. Real-time is the big deal this year. We've also been working on Viewport 2.0 in Maya as well. This is where you can basically have better representation of Redshift shaders in Maya Viewport 2.0, so we're slowly porting those over to HLSL. And we also have some future integrations on the cards as well. So we've been getting lots of requests for a Blender plugin, and we're also considering Rhino too. So throughout the year, we tend to add new features and things, and this is some highlights here. We added a triplanar shader last year, and this is a really neat little shader node. You add it into your shader graph for a material, and what it does, it projects UVs on each axis based on the object's topology. And this is great for if you have very difficult to unwrap geometry for traditional UV baking. And because we actually have 3 different textures for each axis, you can do cool things have different textures for say a mountain with snow on top, something like that. Now this works with bump and displacement maps too. You don't have to do anything special, it just works. And also it works with root pose data. Now this is when you have deforming geometry and want the UVs to actually stick to the geometry and not swim. Very important. Trace sets was something that we added late last summer. And this is for power users out there. This means that you can control what objects rays can see for reflections and refractions, and subsurface scattering coming soon as well. And hot on the heels of this technology, it allowed us to add some cool little features that have been requested over the years. For example, we've been able to include only the caster for AO rays and SSS rays. Custom AOVs, this was a big one that came out late last year in December. Now, I don't know if you were here at GTC last year, but we announced this. We talked about this quite a bit, but we decided to deviate from that plan in the end and actually simplify the shader set that we were going to bring out. So what we've done is we consolidated it, so now you can have basically a beauty pass-through and also write to multiple AOVs at the same time from within a shader graph. That's with one single node. And this code basically added the building blocks for the other AOV technology that we're going to be talking about in a second. And we also added the Redshift render view. This was a big one, very important. With that came like better interactivity and also like open color IO support. This is for like a lookup table, so you can do like cool like gamma correction. And also AOV visualization. This is so you could see the AOVs as they're being generated in the viewport without having to go to like a third-party app and see them first. So throughout the year, we had new features, we fixed bugs and stuff, and we also tried to make general improvements over the features that we already have. And sometimes we get rid of ones that we don't want anymore. Our normal mapping shader, goodbye. So way back when, Redshift 1.0, we had a normal mapping shader. We thought it was fantastic, but not many of our customers did. They thought that it was too XSI centric, and they didn't want to like be limited to XSI style controls. They wanted to be able to use like the texture sampler in their DCC instead, and with all the kind of bells and whistles that it comes with. So what we've done instead is we upgraded our bump map shader to allow both normal mapping and bump mapping. So this means that you can do like UDIM, UV tile. This was previously impossible on our 3ds Max plugin. And also you can tweak mip-maps as well with the texture sampler, so you can get like maybe like sharper bump maps if you want. And this is a very simple thing to do with the new bump map shader. You basically can have like a toggle. You can either choose between traditional height maps or normal maps, and it just works. So another improvement is to our object-based matte option. So with Redshift, you can basically tag an object and turn it into a matte object, and also like a matte shadow receiver as well. So we basically added this for Raymarch volumes last year. That was something that was requested by Blizzard, and very important to them with a comp. And we also had to tackle the problem of like shadows from other mattes. Now what I'm talking about is, normally, at least is what we hear, is that when you have like one matte object casting a shadow on another matte object, you don't want it to actually receive shadows in the matte. So our solution in the past was to say have like a no self shadow option. And that kind of worked for like most cases, but some cases it did not work at all, and actually very simple looking cases. And I'll give you a little demonstration here what I'm talking about. So here we have some delicious programmer art. It's like a nice little box room with a window punched out in it and a sphere in the middle. And we have like a light shining through that window on the sphere, and you can see the light on the ground with a shadow of this sphere being cut by the window. So let's turn this box object into a matte object, and let's take a look at its shadows. So what you can see here is like a very undesirable effect. You actually get the shadows from the box wall actually casting on itself. You don't want that, you just want the shadows of the sphere. So the old solution was to make it a receive no self shadows. So you can do that, and it's amazing. The shadow from the wall is gone, but the sphere now looks wrong. Like, where's the window gone? You don't want that. It doesn't look right. So this is something that we'd received many bugs about, and we had to fix it. So we added a new option, which basically means that you just check this, and it will not receive matte shadows from other matte objects. And this is what it looks like. So now the matte shadow is correct. It's actually getting cut by that window. We mentioned this briefly last year as well. We wanted to improve puzzle map performance in Redshift. So basically, we used to get these questions a lot, like when you have like many puzzle maps in flight. Why was the rendering time like terrible? Well, the answer was rather embarrassingly that we actually approached this rather naively. For every puzzle map AOV, we would re-render the scene. And so this means like more shading, more tracing, and in some cases more texture sampling. So that's actually very slow. So we've actually done away with that kind of multipass approach. So now our puzzle maps are actually generated concurrently with the beauty, and consequently they're now almost free. And just like whenever we go in there and we start modifying the core, we like to see if there's any other things that we can improve. So this gave us a good opportunity to actually improve the performance of indirect lighting as well, which speeds up rendering. And this technology lay the foundation for more exotic AOV technology to come. Okay, more exotic AOV technology, light group AOVs. Now this is something that many special effects studios have been asking us for. And what this means is you can separate light contributions out from each light in the scene, and you can write them to AOV files. Then you can bring those AOV files into like comp package, and you can like tweak the lighting for individual lights without having to re-render in the DCC, which would be slow. So this is a very powerful feature, but it's very easy to set up in Redshift. Basically the way it works is this: you basically invent like a light group name, you assign that to all the lights in that group, and then you assign that light group name to your AOVs for lighting. Now these AOVs can be like separated between direct and indirect lighting, and for different ray types as well. So that means you can separate diffuse from specular and GI from scene reflections. And because you capture all that indirect lighting properly, it means you get the full lighting solution. So you can take all those AOVs, you load them in your comp package, add it all up together, and you get the beauty. It's that simple. And as with the puzzle mats that I was just talking about, these AOVs are generated concurrently with the beauty, so no multiple passes or anything like that, which is slow. And when we last did some performance tests, we found that this was actually no more expensive than generating regular AOVs. Another big ticket item, ray trace subsurface scattering. So Redshift from the very beginning, we always had like a point-based subsurface scattering solution, and this is fantastic for getting like really clean looking renders very quickly, but it does have its shortcomings. For example, point-based is not very good at capturing like fine geometric detail, or if like geometry is too close together, the points can get confused. Or if you have like animations as well, sometimes you can get these edge cases where you would see some flickering. Well, ray trace subsurface scattering doesn't have any of these problems. And also, ray trace subsurface scattering is needed for progressive rendering for like IPR. We've had quite a few bug reports from new customers that have come from a progressive rendering workflow, and they try subsurface scattering and they say, hey, here's a bug. I made this object subsurface scattered and it looks just like regular diffuse rendering. It doesn't work. Well, that was because point-based solution did not work with progressive rendering, but now it does, so no more bug reports like that. Thank you. Another question that we get asked is, how much slower is our ray trace subsurface scattering solution compared to point-based? Well, the answer is that it depends on the scene, but we basically engineered like a very high-performance importance sampling technique. This is so that you can get basically you don't want to waste any samples. You want to basically pick the points that matter, and with proper energy conservation so it doesn't look incorrect. And this is very important for multi-layered subsurface scattering, which is typically used for things like skin. Another thing we wanted to do was make sure that the results were comparable to point-based. So on our materials, you can actually switch between a ray trace solution or a point-based. So it had to be very important that they actually look very the same. And we actually achieved that, but with one caveat. Our point-based solution actually does some area normalization technique. Now, what this means is that you can have an object with different size, and you can scale it, and the density of the subsurface would actually look the same. This is not actually correct, but we left it in from the very beginning because we thought it looked nice. But because it's not physically correct, our ray trace solution does not do this. And finally, we wanted to make this flexible. So when we engineered this, we wanted to make sure that we could add new SSS profiles really easily without very minimal programming effort. And this is something that we managed to achieve. And this is going to be very important in the future when we open up our shader SDK for people out there to actually write their own subsurface scattering profiles. And this will all have correct importance sampling as well without much work. Another big ticket feature, denoising. So everybody's talking about it. Admittedly, we dragged our heels a little bit on this one. We do importance sampling, and GPUs have incredible horsepower. So why would we need a denoiser? Well, the story doesn't end there. Redshift is fast, but denoisers can add that final bit of polish on a frame, especially ones that are very difficult to clean up, really stubborn ones. So we wanted basically, if we were going to have a denoiser solution, we wanted a denoiser that could actually do production quality renders, very important for us. And no denoiser solution is perfect. It can't work miracles. You do need quite a few samples to get the best looking results in the first place. And so in the end, what we did is we chose two denoising solutions for Redshift. First up is Altus by Innerbright. So way back when, I think it was GTC 2015 or maybe SIGGRAPH, we actually met the founder of Innerbright, and he showed us a demo and we were impressed, and we kept on talking, and now it became basically the first denoiser integrated into Redshift. Now, Altus uses basically tried and tested algorithms like wide filters, but they do have some extra secret sauce, which makes it, in our opinion, the best denoiser out there compared to other denoisers. And this means that it's what we think is like the best for production quality rendering. So Altus is able to handle like really heavy scenes, and also it's able to handle animations as well, which is very important for us. And very importantly, Altus is available at a deep discount for Redshift users. So if you're interested, you can visit their website and you'll see. So here's a little example here. On the left, I believe, the left, that is a toaster rendered with 128 samples, no filtering. You've got some depth of field in there, and as you can see, it's very noisy, looks nasty. And on the right there, we have like Altus. It's done some denoising. You can see that it's preserved the details on the surface there, and it's gotten rid of some of those nasty noise in the blurry depth of field. The second denoiser that we integrated with is Optics. Now, Optics AI denoiser by NVIDIA is magic. And what do I mean by that? Well, they don't do the kind of like filtering algorithms that Altus does. Instead, they use AI and deep learning to best guess what an image should look like. So when NVIDIA told us to test this, they told us that basically it's been trained for many, many hours with really, really high quality Iray renders. And so we were kind of skeptical, like why would Iray renders work well with Redshift? But we tried it and we were very impressed. The results were very good. It was fast, and it did manage to get rid of some of that nasty noise as well. So we think that this is going to be a really great tool for like previs and certain stills rendering. And once we actually get some Redshift data in there to like train it, we think you're going to get even better quality as well in the future. And here's an example. Same old toaster, very noisy on the left with the depth of field, and then we've got like our Optics solution there, and as you can see again, it's managed to like preserve some of the patterns on the surface, and it's like gotten rid of some of that nasty noise on the depth of field effect. And I don't know if you guys know, but like both of these denoising solutions will take AOVs as well, so you can like best describe what the surface should look like, so that helps it steer the denoising effort so it doesn't blur things that shouldn't be blurred. So we have some more features coming up in the future. This is actually probably next week actually. Global volume shaders. So basically we have like this, we have global volume scattering and fogging. And so we've basically opened up the shading so that you can actually like add 3D procedural noise textures to the scattering component. So you can do cool effects like clouds and things like that. Now, I should mention that this does not work with transmission, the actual like fogging effect, because that involves ray marching, which is slow. It's complicated to get right and fast, but it's something that we've not ruled out. So when we open up our shader SDK, we're going to be tackling that as well, and we hope to get that working too. Cryptomatte, this is also coming very soon, next week probably. And now this is developed by Jonah Friedman at SciOp, and this attempts to solve the matte coverage problem. Now what I mean by that is when you have like matte images, and you have something like depth of field or like heavy anti-aliasing filtering, those images get blurred together, which are very difficult to deal with in comp. Now the Cryptomatte actually deals with that at a subsample level, so a lot of our customers are very happy that we're adding this. An area light spread barn door effect. So this is where you have an area light and you can sort of like focus the lighting like a spotlight. Now this is something that we sort of said we were going to do last year, but we kind of got tied up with other tasks. We haven't forgotten about it, we know it's important, and we'll be adding this shortly after the GTC. So the future, always more features. Toon shading, another important one. So right now we're talking to one of the top animation studios in Japan. They basically know how to make CG anime that actually doesn't look CG, really high quality stuff. So the first thing that we have to do is basically solve all those problems in the core, and once we've done that, we're going to get a really, really nice Toon shader out to you guys. LPEs, light path expressions. This kind of like complements the suite of custom AOV technology that we're talking about. This means you can sort of programmatically say what kind of AOV you want from, say, which depth bounces and stuff like that. It's crazy stuff, really hardcore. Maya Fluids is something we're going to be doing soon, and XGen IGS. And also Redshift 3.0, it's coming sooner than you think. So Redshift is already very fast, but we want to make it faster. And we've had some very good ideas about how to do this. We've been talking about this for years, actually. So this is going to involve like some refactoring of the core technology for like tracing and shading. And when we do this, we're not only going to make it faster, we're going to be getting rid of the trace depth limit that people have been complaining about. Right now it's 16, and that's no good for things like hair, like glasses and stuff like that. We've got these glass objects and windows, like architectural scenes want more trace depth. So we're going to be getting rid of that limitation, and we're going to be making it faster as well. That's just transparency I'm talking about too. So better performance, more intelligent sampling. We want to be able to get rid of all the kind of different like settings for samples and all that kind of stuff. We want to make Redshift actually choose the best sampling rate for you to get the best results the quickest way with minimal effort. And that's something that I think we mentioned it a little last year, so R&D. Distributed remote rendering, that's something that we have also planned for Redshift 3.0. And also the mythical shader SDK, which we talk about every year, but we never actually do. We are going to do it this year, I promise. 1 minute. And when we do that, OSL support will come after that, which is something we're really interested in supporting, as well as MDL. So that is it from me. Thank you very much.